Okay, so we are pleased to have Alankrita here with us today. She did her PhD from UC San Diego, advised by Professor Yong Han Kim. And after that, she was a research fellow at Simons Institute for the Theory of Computing at UC Berkeley for a while. And currently, she's a postdoc at the CMS department at Caltech. She has worked on information theory and statistics and currently sequential decision making, and she's going to tell us about universal probability and applications to data science today. So we are pleased to have you here, and over to you.
Thank you so much. Thank you to the organizers for the invitation, and thank you all of you for being here. So let me share my screen. All right, so everyone can see, right?
Yeah, we can see.
Okay, great, thank you. Yeah, so I'm excited to tell you today about the universal probability approach and illustrate the utility of this approach via some example applications. Right, so let's get started by looking at this wise quote by Laplace, who also told us that the probability of the sun rising tomorrow, if it has risen continuously for n days, is given by n+1 over n+2. And one of the aims of this talk is for me to convince you that there is a principled reason why it must be so. Right, so the sunrise problem and many other problems that we're interested in can be encompassed in the general framework of sequential decision making, where given some historical data, y1 through t-1, we need to take an action A for the upcoming data point in order to minimize some loss. Right, so if we know the distribution generating the data, the optimal action to take is called the Bayes response, which basically is simply the action that minimizes the expected loss function, right, for the upcoming data point. But of course, you might have already seen the challenge in this approach, which is that usually we don't know the distribution that underlies the data, and the decisions that we take need to be taken in a purely data-driven manner. So what the universal probability approach advocates for is to construct one single probability measure Q that is approximately equal to p theta for all the distributions within this class capital theta, right? So construct one distribution that is an approximator for every distribution within this class. And how do we use it for decision making? We just pretend that the data is coming from this universal probability measure and take the Bayes optimal action with respect to this universal probability measure. If indeed this Q is a good approximator for every p theta, you expect that you wouldn't lose too much. Now, of course, the questions are, can we construct such a Q? Does it even exist? And what are the uses, if any, of this Q in practical engineering problems? Great, so that was all a bit abstract. So for a concrete example, to illustrate this approach, we're going to look at universal compression. So compression was not only one of the first use cases for the universality approach, but considering this is also going to lead to a very nice, precise definition of universality, which has a very strong operational interpretation, right? So let's say we have a sequence yn, for simplicity, let it be binary, generated from some distribution p theta, which is not known. And our task is compression, which I'm sure many of you have already studied before. So for each each sequence 0, 1 through n, we need to come up with a binary string to describe it. And since this compressor has to be lossless, we want to be able to reconstruct yn exactly from the compressed representation, which means that this mapping has to be 1-to-1. And the task here is to come up with a lossless compressor that has the lowest expected length possible. So intuitively, what you want to do is assign a larger length to highly unlikely sequences and a lower length to very likely sequences. Right, so now you can assume that we can't have a very, very low length compressor while it is still lossless. And indeed, there is a fundamental lower bound we have for any lossless compressor, which I'm sure many of you have seen before. This is the entropy rate the entropy for IID sequences. And our task is to come up with a compressor that matches this fundamental lower bound. Right, so if the distribution of the data, this p theta, is known, then there are many ways to construct a compressor that gives us length for a sequence yn that looks like something like log 1 over the probability of that sequence, right? So, and for such a compressor, the expected length is basically the expected log 1 over p, which we know is the entropy of yn. So if we know the distribution, then we know how to construct, optimal lossless compressor. But now the task is to do this even without knowing the actual distribution generating the data. Right, so now is a good time to define universality. So a distribution Q is universal for a class of distributions capital theta if the KL divergence between any p theta in that class and Q is sublinear in the block length. And we want this divergence to be uniform over all theta, right? So Q can approximate every p theta in the class in sub KL divergence sense, right? So let's say we have a probability assignment Q that is universal for this class theta. Now, can we construct a compressor out of it? Yes. So let's say we have such a Q. So we have a QYN that is universal. And I just want to mention that if you have a Q for the whole sequence, you can easily come up with a sequential probability assignment, which is just by using chain rule of probability. So often the sequential and this whole probability assignment is taken interchangeably. So let's say we have some kind of sequential probability assignment for the next data point given the previous data points. And how do we convert it to a compressor CQ? We can do this by using a method known as arithmetic coding, in which we just put in these probability assignments, and this ends up giving us a code. And this code we can show has expected length entropy of yn plus this mismatch term, which is the KL divergence between the actual data generating distribution and the distribution which we've put into a compressor, plus some constant number of bits. So you might have also seen this before in like mismatch source coding. This is the extra length you must incur. Right, so what happens when we take this whole expected length divided by n? This term is going to go to the entropy rate. This term is going to go to 0. And this term, by virtue of Q being a universal distribution, is going to go to 0 also, right? So in this case, we went from a universal probability to an asymptotically optimal compressor. And we also saw why universality is defined in this way, right? Because operationally, it's the extra length that you must pay for universal compression, right? So that was the definition of universality, but I still haven't shown you how to actually construct a universal probability distribution, which I'm going to do now. So
may I ask a quick question?
Yes.
Hi, this is Prakash Narayan. That
Hello.
H was computed according under P theta, right? Or Q.
Yes.
Okay, all right,
according
thanks.
to the.
Yeah, thank you.
Okay. Right. So now I'm going to try to construct a universal probability assignment for the class of all Bernoulli IID sequences. So I have Bernoulli IID sequence with theta varying anywhere between 0 and 1, and I want one Q that is able to approximate every single p theta for theta in between 0, 1, right? And I'm going to show you a construction for a universal probability in this case. So a very simple and intuitively appealing idea is to just take a mixture over all of the distributions that are within this class weighted by some appropriate prior W theta, right? So we kind of expect that since this Q is an average of all of the P's in this class, it's a little bit of everything. So we might expect that, this Q might be a good universal approximator for this class. Yeah, and it turns out that this idea is pretty powerful and it does work in this Bernoulli theta case. So let's take a look. The simplest prior that we can think of in this case is just take W theta to be constant, a uniform prior over the parameter theta. Right, so in this case, what we end up getting is something called the Laplace probability assignment, and you'll see why it's named after Laplace. So for any binary string 0, 1 through n, the probability assigned by this assignment to yn is the probability assigned by an IID Bernoulli theta probability distribution integrated over all theta. Right, so this is p theta yn. We just integrate this over all theta. And by using some property of beta functions, we end up getting this expression where k is the number of ones in yn. This is much more illuminating if we write this down sequentially. So what is the sequential probability assignment that we get in this case? So the Laplace probability assignment will tell you that the probability of seeing a 1, if you have seen kt once so far, is proportional to kt plus 1 over t plus 2, is equal to kt plus 1 over t plus 2, right? So now we can see why it's called Laplace, because if you have seen only once so far, if the sun has risen continuously for n days, the probability of seeing the sun tomorrow is going to be n plus 1 over n plus 2. Right, so to vindicate Laplace, we need to show that this is a universal probability assignment, and that's not very difficult to do. So let's see. In this case, let's write down log p theta yn over q Laplace yn, which is equal to theta to the k, 1 minus theta to the n minus k over times n choose k times n plus 1. Right, from this representation of the Laplace probability assignment, this one. And this is just going to be log n plus 1 plus log theta to the k, 1 minus theta to the n minus k times n choose k. And this is a binomial probability of k successes. So probability is always less than 1. So this is always upper bounded by log n plus 1. Right. So we can see that the Laplace probability assignment is universal for the class of IID Bernoulli theta distributions, and it achieves at most log n divergence. And in fact, it achieves something stronger than divergence, because it achieves like the max log likelihood ratio is bounded, not just the expected log likelihood ratio. So this is a much more stringent condition for universality, which this assignment satisfies. Right, so that kind of illustrates the utility of the mixture approach, which we'll come back to also later. Right, so that was a simple but very important class, but there have also been constructions of universal assignments for larger classes than Bernoulli IID sources. So for example, context tree weighting, which creates a universal probability assignment for the class of all variable order Markov or tree sources, and the Lempel-Ziff probability assignment, which can construct a universal probability assignment for a class as large as like non-parametric stationary ergodic sequences. Right. So now that hopefully I convinced you that you can actually construct such a universal probability assignment, let me tell you a bit about applications of universal assignment in practical problems. So, of course, the first and the most significant application that we have already seen is compression, and one of universal compression, and one of the most significant results in this area that we use every day is the Lempel-Ziff compressor. It's very useful in things like denoising. So for example, when you're trying to denoise an image without knowing the statistics of the distribution generating the image, it's very useful in entropy estimation, for example, which comes up a lot in scientific applications. And of course, it's very useful in sequential prediction, which is known to have very close ties with compression. Right, so some of my own work in this direction has been along a few lines. So for example, I've worked on compression of large graphs, which have complex two-dimensional correlation structure for which current methods don't readily apply. I have worked on prediction and learning with the log laws, and we will see, this is actually going to come up later in the talk, the log laws. And I've also worked on on an application in finance, which is portfolio selection with site information or hints. And I'm going to go into this application in more detail and show how the ideas developed in this universal probability approach can be useful in solving this problem. Okay, so before I dive into portfolio selection, I'll just take a pause and ask if there's any questions so far.
May I ask a question?
Yes, of course.
Now, you use the universal prior. There are other priors that are used which come from the
Yes.
conjugate priors. So you could have the Dirichlet prior, for instance.
Exactly.
And,
yeah. So
and what's the trade-off?
yeah, that's a great question. So the reason I chose Laplace was because it's the easiest to
Sure.
show some results for, but there is actually a principled way to choose the prior. And in fact, for this, one should use the beta half-half prior, which is the Dirichlet prior, as you're saying.
Yes.
And the asymptotically optimal prior to choose is the Jeffreys prior in general, which is given by, W theta is proportional to square root the determinant of the Fisher information matrix. So, and in fact, if we use for the Bernoulli IIT case, this just turns out to be the beta half-half prior, the Jeffreys prior in this case. And that will give us the asymptotically min-max divergence, which is equal to half log n. So you get a factor of half. So this is optimal, including the constant.
I've lost track of this line of work, but I remember also that in some cases, here, for instance, you could compute this upper bound on the expected redundancy, which is what this divergence is. And you could do it just by hand, but sometimes it becomes messy, and then you sometimes one uses a Taylor series expansion. And does that come up in what you're going to do?
No, so we're not going to be very concerned with the
I see. Okay.
All right. Yeah.
Okay.
So because we are more concerned with actually getting order-wise results at this point rather than sharp results like in this case. But you're right. The Taylor series stuff will come up, for example, in the proof of showing that the Jeffreys prior is asymptotically least favorable for this entropy.
Right.
So in that case,
Yeah. Okay. Very good. Thank you.
Okay. Yeah. Anything else?
I had a quick question. So it's like maybe not directly related, but so you defined this Laplace, this distribution that you got, right? So based on this expected, like the redundancy rate of it. Are there like other characterizations of these? So if I do not go through compression, if I want to get at that sequential distribution that you had directly,
I see.
Are there other characterizations of it? Like, does it have like other nice properties?
Yeah. So usually, I haven't seen anyone come up with another definition for universality based on something else. But one thing that you can show is that using universality from the definition of universality that operationally comes up from something like compression also suffices for a lot of other loss functions. So for example, in this paper, there is this one, there is a very strong result that if you have a universal probability assignment, which approximates in terms of KL divergence, you can just use it for any bounded loss function. So yeah, but I haven't seen other definitions coming up from like other operational considerations.
I see. Thank you.
One more quick question. How does this compare with, for instance, a min-max? So you would be taking an inner minimum, I'm sorry, inner maximum with respect to theta and outer minimum with respect to Q, right?
Yes, yes.
Now, how does this compare with that? The rate is the min-max.
So min-max is half log n for
half
this
log n,
problem.
okay.
Yeah.
In this particular case, right?
In this particular case, and also for arbitrary alphabet size. So for arbitrary alphabet size, it's m-1/2 log n. So the mnemonic is half log n for degrees of freedom.
Sure. So that is because the family has, in this case, every theta corresponds to an IID measure, right?
Yes, yes.
Now, there is also the other approach, which you didn't mention, the minimum description length approach to Kia. And that also gives you the half log n and associated terms. Does that can that method be used here in directly the minimum MDL principle? So you write the main cost function plus a penalty term.
So
the reason I ask is, so here the applications you mentioned, compression, denoising, entropy, estimation, prediction. Now, I know there's also been some work on order estimation. So for instance, sorry, if you're given a Markov family, then the same set of ideas can apply, and you can have a prior which then gives you a way of computing the probabilities in a sequential way, very much like this, because you can get the conjugate prior, and then that idea is used for order estimation. So what's the underlying memory of the Markov process, for instance, right? To estimate the, and then the minimum description length principle has been shown to play an important role. So I was wondering if you have looked at those applications as well, but from what you've written here, yeah, sorry, go ahead.
Yes, no, sorry. So I'm less familiar with the MDL approach, but I know that it has some, definitely some connections to this idea of using the Dirichlet prior and then, showing that the Dirichlet prior is min-max and so on.
Yeah. So there is actually an excellent tutorial which appeared in the IEEE Transactions on Information Theory way back in 1998. And unless I'm mistaken, this was authored by Jorma Rissanen, Bin Yu, and Andy Barron. And that deals with the minimum description length principle applied to a number of applications. It might be worth just looking at it for as a reference. Yeah. All right, sure, welcome.
So one more way of getting something like the Laplace probability assignment, if you like think of more the kind of the methods people use in online learning that I know of, is basically the following. So let's say you have y1 through t, and you want to pick some theta for the next one. So if you try to so if you try to choose the theta that minimizes this, so this is something called FTRL, so follow the regularized leader. So for example, this is the so this is the loss that the theta will obtain so far, plus this is some regularization term. I believe this also gives you the same add one probability assignment. So this is some kind of regularization view that is more prevalent in like the online learning kind of community. I don't know if this is related to the MDL stuff.
Interpretation for the MDL principle is you write the log likelihood ratio, and then is the number of penalty term is number of free parameters by 2 log n or something. Yeah, it was something like that. So here the number of free parameters would be, in your IID case, would be the alphabet -1, because in this case 1, as you said. In general, alphabet size -1. Yeah, right.
I see. Okay, yeah, but thanks. That's a good point. Okay. So let me just start on the portfolio selection problem. So I'm going to start with explaining the original problem as formulated by Cover, and then explain how we are going to incorporate side information into this. Right. So to motivate this problem, think of investing in a stock market where at the beginning of each day, you choose a distribution AT over M stocks. Right. So for example, you could choose to allocate your wealth uniformly over all stocks, or you could choose to allocate your wealth a little more on stock 1 and less on the other ones, and so on. Right. So at the end of the day, after you've invested, you get this vector of price relatives, and each component of this vector represents the ratio of the value of that particular stock at the end of the day to that at the beginning of the day. So for example, if XT1 is 1.1, it means that all the money that you had invested in stock 1, the value of it has gone up by a factor of 1.1. And if this is 0.9, then the money that you invested in this stock has depreciated, the value is depreciated by a factor of 0.9. Right. So at the end of the day, the ratio of your wealth at the end to that at the beginning of the day is given by the fraction that you had invested in each stock times the value by which that stock rose or depreciated, added up over all stocks, which is just A transpose X. Right. And our goal here is to construct a portfolio selection strategy A to invest continuously over N days. So portfolio selection strategy is essentially a sequence of functions that's going to take in the price relatives observed so far and give you a distribution over the M stocks as to how you should allocate your wealth. So for example, a good strategy which has seen that the stock 1 has been performing much better over the past few days is going to allocate a higher value to that particular stock compared to the others, for example. Right. And if you invest continuously for N days, the ratio of your wealth at the end of N days to that at the beginning before starting investment is just going to be the product of these ratios, the wealth at the end of each day to the beginning of each day, right? And our objective is to make this wealth ratio factor as large as possible, right? So one example, perhaps the simplest example of a portfolio selection strategy is constantly rebalanced portfolios, where every day you choose the same portfolio, regardless of what the history is. Okay. So now we know that the wealth attained, this is we call the expression for the wealth attained by any strategy. So now I'm going to define the exact task. So the class of all CRPs is a good reference class to be able to compete against. So the task that we're going to set for ourselves is to come up with a portfolio selection strategy, a causal portfolio selection strategy that takes in the price relative seen so far, and that achieves a sublinear log wealth ratio compared to the best fixed CRP in hindsight for any sequence of input vectors, for any sequence of outcomes. So what this means in English is that if the best CRP in hindsight is able to achieve an exponential wealth increase with some positive exponent alpha, then we want a strategy that is also able to achieve an exponential wealth increase with the same factor alpha, possibly up to some lower order terms. And we want to do this without future knowledge, right? This one is using, this one is a non-causal strategy because it uses the entire sequence once. So this is the task. And we can write this in another way that is more familiar if you work on no regret online learning. So if we just substitute the expression for this Sn here, the log of product will just become a sum. And the task here becomes online convex optimization with this particular loss function. And we want to achieve no regret for the worst possible sequence of outcomes compared to the best fixed action in hindsight, right? So this is, and the reason that this is more challenging to deal with, this loss function, is because it's not bounded and it's not Lipschitz, which are assumptions that in online learning you usually see. So this is why standard methods, like for example, you can't use online gradient descent here. So we need to come up with some other method to deal with this loss function. Yeah. So
I have a quick question. Could you show
yes.
the constantly rebalancing strategy, what it does?
Oh yeah. So the constant rebalancing strategy just picks a fixed vector every day. It invests, like for example, you're going to allocate uniform fraction of your wealth every day.
Yeah. So so the hindsight doesn't. So the hindsight is only in that, okay, like this particular fixed allocation is the one that maximizes.
Yeah.
Okay.
Yeah. So we are we're going to compare against it, right? So we are going to say that I want to match the wealth attained by the hindsight optimal up to this first order in the exponent. So that's going to be our benchmark strategy. Right. So okay, so this is the classic portfolio selection problem you look over. So now I'm going to introduce side information, and like Sagnik was mentioning, we're going to try to strengthen the benchmark so that we have a stronger benchmark to compete with and try to come up with a strategy that can compete with the stronger benchmark. Right. So let's say now at time t, you have some extra side information zt. So now the action that you need to take is not just dependent on this, but also the extra side information. And this could be anything. For example, it could be the truncated history of the market itself, but it could also be something extra that gives you a hint about XT. For example, it could be like in Hong Kong, if you're in Hong Kong, it could be the price relatives of the New York market yesterday, for example, right? So now the extra thing that we're going to assume, the model here, is that there's going to be a state function that is going to map the side information Z to a state S, to a state from 1 through S. And this state function is unknown to the investor, right? And this state function could codify something like, is stock 1 going to do well today or not? So, and the fact that the state function is not known to the investor is what makes this problem a bit more challenging. So for example, there's the old work by Kober and Ordentlich that assumes that there is just one state function, or that everybody sees the state directly. So, but we are going to assume that there is this state function from this class. We only know this big class, but we don't know what exactly the state function is. And now we are going to strengthen the benchmark and try to compete with the stronger benchmark. So now the benchmark has both the flexibility of knowing state function and adapting state-wise CRP. So earlier, the benchmark was fixed to have a fixed portfolio at each time step. But now the benchmark has allowed the flexibility of changing the portfolio according to the state. So for example, if the state function is encoding whether the price relative 1 is going to do well today, then the CRP on the days when the when the stock 1 is going to do well should allocate more wealth to stock 1, right? So now again, the regret is going to be the same. So this is the this is the portfolio obtained by a state-wise CRP, and this is the portfolio of the investor. And again, we want to achieve the same log wealth ratio. And this strategy, because it's stronger than the CRP, this is going to achieve wealth greater than the CRP. So we are going to try to compete with this benchmark that can attain a higher wealth. So as a concrete example, the side information could be yesterday's price relative, and the state function class, let's say we could have 2 states, and the states could encode whether or not stock 1 is going to do well today. And this is going to be based on whether yesterday's price relative for stock 1 was good or not. So for example, if yesterday's price relative for stock 1 was high, I can reasonably expect that it's going to be the same today. But I don't know at what threshold this is true. Like if if stock 1 doubled in price yesterday, I might assume that it's still going to be good today. But maybe if it went up by 1.001, it's not, reasonable. It's not a reasonable thought. But yeah, so we don't know the threshold beyond which we can comfortably assume that yesterday's price relatives gives us a good measure of how today's stock 1 is going to do. So the task is to compete against the best state-wise CRP that is using the best state function that fits the best data from this class. Okay, so yeah, this was the model. So if there's any questions, I'm happy to clarify now. Okay, shall I go ahead?
Yeah, I guess so. There are no questions in the room.
All right. Okay. So, all right. So far, we've seen this formulation of the portfolio problem, but it's not really clear where universal probability is going to come into the picture, right? So now I'm going to try to explain why there is this, where this universal probability assignment actually comes into the picture. And I'm going to show this in the case of no side information, because that's much easier and it's got all the basic ideas covered there. So yeah, so first of all, we're going to have some notation here. So x of y1 through t is going to be defined as the product of the ith component of the y-ith component of the ith x. So for example, x21 is the second component of x1 multiplied by the first component of x2, right? So this is 2, 1, second component of the first x multiplied by the first component of the second x, right? So this is x21 is the basis vector 2 multiplied by x1 times basis vector 1 multiplied by x2, right? So this is the wealth obtained by the investor who is doing something a bit foolish and investing all of her money into stock 2 on the first day and stock 1 on the second day, right? So this is wealth obtained by extremal investor who is, right? So, and similarly, we can have a similar notation for A. So now I'm going to write the wealth obtained by any portfolio A in a slightly different way. And this is just going to be like writing a product of sums as a sums of products. So you'll see what I mean if I just write this as, let's say we have just 2 time steps, right? And this is A11, X11, A12, X12 times A21 plus A22, X22. Right, so in this example, let's just take only 2 stocks for clarity. And if I open up this product, I'm going to get 4 terms, right? So for example, I'm going to have A11, A21, X11, X21, A11, X11, A22, X22, plus 2 other terms. Right, so this is right, because I'm just using the distributive law here to collect these terms together. So this is first component of A1 multiplied by first component of A2, first component of X1 multiplied by first component of X2, and similarly it's first component of A1 multiplied by second component of A2, and so on. Right, so if I have n of these, I'm going to have 2 to the n terms, and that's basically what this is, just collecting all of these extreme terms together, right? So yeah, this is just a different representation. Now let's try to write this down for CRPs. So let's say we have a fixed CRP B, right? Because we have only 2 stocks, I can write any CRP as just B1 minus B with slight use of notation, right? Because we have only 2 stocks, you have to figure out how much you're gonna allocate on stock 1 every day, right? So in this case, what is B of yn gonna be, right? So this is BT of Y, sorry about that. It's gonna be B TYT product, right? Because all of the B's are the same. This is just going to be B of YT, right? So each of these is going to be B or 1 minus B, right? So I can just collect this. This is going to be B to the power number of 1s in Yn times 1 minus B times number of 2s in Yn. And this is exactly the probability of a Bernoulli B distribution on this sequence, this binary sequence, right? So this is kind of showing where this probability idea is going to come from, because we're splitting up our wealth into the wealth obtained by these extremal portfolios, and the weighting in front of that extremal portfolio is going to look like a probability. So in particular, if we can come up with a strategy A that is able to achieve such an expression. So let's interpret what's going on in this expression here, right? So this is sometimes called a fund of funds expression, because like I was mentioning over here, X of Yn is the wealth obtained by an extreme investor who is investing all of its money on Y1 on the first day, then all of the money on Y2 on the second day, and so on, right? So how you can interpret this expression is, let's say you have, because there are going to be 2 to the n of these terms. So let's say you have 2 to the n fund managers. Each of the fund managers has this extreme portfolio strategy, and you are, let's say, investing $1. So you're going to give a fraction of your $1 to each of these extreme investors, and the fraction in which you're going to allocate your $1 is based on this Laplace probability assignment or any other probability assignment for that matter, right? So if we can construct this type of strategy, then what we can get is basically that here's what we get. So let's write down the log wealth ratio. This is the log wealth ratio attained against any CRP with the wealth ratio, with the wealth of our strategy, which we are allocating our wealth, according to this Laplace probability assignment. So now over here, we're going to use the fact that for positive numbers A and B, the ratio of sums is always upper bounded by the maximum ratio of the terms. So we can go with this later. So now I'm just going to upper bound this by max over yn, the maximum term with the maximum ratio, and the x's are just going to cancel out, right? So what I'm going to end up getting is b of yn divided by q Laplace of yn. And b of yn is just like probability assigned by any Bernoulli B distribution on this yn sequence divided by q Laplace. And like we saw earlier, the Laplace probability assignment is universal in this even stronger sense of pointwise universality. So this is going to be at most log n regret. And when Prakash was mentioning, if I use the strategy achieved by the Dirichlet probability assignment, I can even get half log n over here, right? So this is the idea here. By converting by allocating our wealth into a mixture of these extreme investors according to a universal probability assignment. And this is how to do this is this idea called a probability induced portfolio. This is like very related to a mixture. So for example, if you select your portfolio to be a mixture, weight it with the right. So if you take a mixture over all of the, so if you take a mixture over all CRPs, while weighting each CRP according to its performance on the data observed so far and some prior, you end up getting this type of a portfolio. So this also comes from mixture. So for example, if I chose this WP here to be a uniform prior, I would end up getting this, for example. So this also comes from a mixture probability assignment. Okay, so that's kind of where we bring in probability assignment into the portfolios problem. And we can do something similar for conditional or side information probability assignment, right? So let me talk about how to do that. So if we want to do something similar for the sequential, for portfolio selection with side information, where we want to achieve low regret against the best state-wise CRPs, we need to figure out what is the corresponding sequential prediction probability assignment problem, solving which can be used to solve the corresponding portfolios problem. Right, so here is the probability assignment problem that we are going to be looking at, because solving this would imply also solving the portfolios problem. Right, so this is probability assignment, again a sequential problem where at each time step t, we have some side information zt that's revealed. And once the zt is revealed, what we need to do is assign a probability to the upcoming symbol yt. So if m was equal to 2 and you had to assign a probability to the upcoming binary symbol, you would say something like, it's going to be 1 tomorrow with probability 60% or something, right? And once the actual symbol yt is revealed, the loss incurred is minus log 1 over the probability to what actually came up. So if you said it's going to be 1 with probability 0.6 and yt is 1, then your loss is log 1 over 0.6. So if you gave something a really low probability and it actually turns out to achieve a high loss here, right? So, and the competitor paralleling the portfolio's case is going to be the best state-wise IID compressor, right? So we have some class of state functions that map from the side information to one of S states. And for a fixed state function and a set of parameters theta 1 through S, the probability that the competitor is going to assign is going to be just theta S, basically, for the upcoming symbol. So for example, if m is 2, then the competitor is just going to look at the state and say that, yeah, it's going to be Bernoulli theta S distribution tomorrow. Okay, so the regret, again, it turns out to be the loss incurred by the decision maker minus the loss incurred by the best fixed, by the state function and the set of probabilities that best fit this data, right? So this is the probability assignment regret, and just writing it down in a shorthand, I'm going to write it down this way. So this term right here is just the product of the probabilities, state-wise, because it's state-wise IID, right? And this notation is sometimes called causally conditioned probability. So it's going to be Q of yt given yt minus 1 zt, ranging from 1 to n. So because it looks like a conditional probability, but it isn't really, right? So it's like you get z1 first and y1, then z2, and then y2, and so on. And you want to find the conditional probability of each yt given everything that came before it, right? So this is the probability assignment problem that we are going to try to solve, because we can show, using similar ideas that we had in the no side information case, that solving this suffices to also solve the portfolio selection problem with side information, right? So now the next couple of slides are going to be devoted to studying this problem, because once we solve it, we just put it in a probability induced portfolio expression and we just get a portfolio strategy directly, right? Okay, so this is the quantity that we want to control, the log probability ratio and the problem that we just discussed. And now I'm going to explain how to come up with a probability assignment strategy for this problem by looking at the simplest case and then adding one layer of complexity each time until I can explain what is our strategy. And it's all going to be based on mixtures. So it's going to be progressively, more and more stuff on mixtures. So, okay, so here it is. So first of all, let's take the extremely simple case where you just don't have any side information. This is something we already saw a lot. This is also the cover case. So in this case, what we want to do is we want to solve this problem, right? For theta, for any theta. And this we saw that we can do with the Laplace add one probability assignment, which is also the mixture, right? U is just mixture p theta. Right, so we're good here. We know how to do this. We put it into portfolio expression, and this is Kober's universal portfolio. Now, let's take the case where we know the state function. So this is the Kober or Dendlich case. So you, instead of getting the Z, you just get the state on each day. So you get state, and then S2, and then Y2. Right? So in this case, we can do something like a state-wise mixture, right? Because let's say I know that on day T, the state is 1. I can just separate it out. I can separate out all the time steps where the state was 1, just look at that subsequence, and then do an add one probability assignment on just that subsequence, right? So that's also good. Like we can do this state-wise mixture. So in this case, we would just, have Q of yn given condition on Zn to be just p theta mixture with respect to all the thetas. And we can do this. We don't need to take any mixture over the function class G because there is only one function in it, right? So, and doing this will in fact give you the same state-wise add one probability. So now we want to add subside information Z, but we don't know what the state function is. So let's say that all of the Z is available non-causally. So let's say all of the side information is available at the beginning, right? So we're not getting this sequentially. We know what the side information is going to be at the very beginning, right? So what we can do in this case to take a mixture over the function class G is to partition the set G into partitions where any two functions within the same partition agree on the side information. So G1 of Zn is equal to G2 of Zn for any two functions within the same partition. So, because we know that this state function class is going to map Zn to some discrete set of states, we know that even infinite function classes can be split into at most s to the power n partitions, although usually any reasonable classes will be split into much fewer than that, right? So now we can partition G into sets that agree on Zn, and once we've done that, we just need to notice that within each partition, the functions are essentially indistinguishable because they agree on Zn, right? So for this problem, they're not any different. So what we can do in this case is just take one representative function from each partition and kind of flatten this potentially infinite class into some finite number of functions, one from each partition, right? And then take a mixture over this finite number of functions, right? So we take our usual, Dirichlet, uniform, whatever mixture on the thetas, and then we take a mixture over this finite number of functions that we have flattened our function set into, right? So this is our mixture. Two layers of mixture, one over theta and one over the functions n. And in this case, what we end up getting is, let's say that the true or the best fit state function is, we know that it's within one of these classes, right? So we know that there is at least one representative in this set of functions that we're taking a mixture over, for which G star and that function agree everywhere, right? So intuitively, like this is not very difficult to show, but not gonna go more into it. So intuitively, we're paying a log n penalty for taking a mixture over n functions, and we have reduced it to the case where we know the state function, right? Because if I use G3 or if I use G star to construct my probability, that doesn't matter because they're both the same anyway for this set of side information that's going to appear, right? So in this case, we can solve this problem also, right? By going back to the known state function case. So
may I just to understand? So
yes,
what
yes.
you do is you have the side information, and then you have the G functions, and you partition the Z's into those atoms on which the G's agree, and then you
The
locally,
opposite.
yeah, and then you
Yeah.
have the local mixture, and then you take an average across the atoms, right?
Yes, yes.
And the average, why the average? Because each of the G's is roughly of the same importance, or it really doesn't matter whether you put some other distribution, you won't change the asymptotics anyway.
I don't think the asymptotics will change if
see.
you
All right.
have any prior over this. But yeah, that's definitely like an interesting direction to think about whether
The question would be, if you have multiple atoms, if somehow it's a large set of atoms, then would the average be the best thing, or you would take some other mixture with respect to something else, right?
Yeah, so we are going to, later when I show the main result, we are going to restrict our classes into those for which there are much fewer number of atoms than s to the n. In fact, if we restrict it to classes with, for example, finite VC dimension type classes, this is going to be a polynomial in n.
I see. So it means that somehow the side information is not too discerning, right? It's discerning, but not too much. Is that what it conveys? Yeah. Okay.
Yeah.
All right, good. Thank you. Yeah.
Yeah, the function class is not too rich. If you consider like the class of all functions, for example, for which you will certainly have s to the n partitions, then you can't do anything.
Of course, sure. Thanks.
Yeah. Okay. So that was for the non-causal case. So now we want to understand how to move from non-causal case to the causal case. So this was, how we reduced it to a log number of functions term plus the regret when you have a known state function. So now the question becomes how to effectively discretize the class of state functions without knowing all of the side information in advance. And a simple idea that we could use here is to choose the side information that we've seen so far as a proxy for what's going to come in the future, and then refine the partition as time goes on in some manner, right? So in this case, the idea is that if Zn is stationary and the distribution across time steps doesn't change much, then we expect that the partition will not be too different. So for example, what would happen here?
Oh, I'm sorry to interrupt. I just, yes. I now know what was, here little n is the sample size. Capital N can actually grow with little n. That's what you would expect for large little n.
Yes, it should. Yeah.
And that was my question. So what do you do in that case?
Yes. So as long as it does not grow too fast, as long as it grows something like polynomially, we are good. If it grows too fast, in fact, if it grows polynomially, we end up getting like a logarithmic regret. If it grows like faster than polynomially, if it's like what's called a non-parametric class, you end up getting like polynomial type regrets.
Yeah, I see. All right. Okay.
So so the kind of geometric structure of the function class does come into play.
Okay. Thanks.
Yeah. So the idea in choosing the history as a proxy for what's going to come in the future is the following. So let's say that we have taken a mixture with respect to, so this is the partition with respect to the history. Right, so we know that if the best state function is G star, best fit state function is G star, we know that there is going to be a function G1, because this is a partition with respect to the history, for which G star and G1 agree on this sequence. Right, so the question now becomes, if the Hamming distance between this sequence and this sequence is 0, what can we say about the Hamming distance between Zt to n and G1 of Zt to n, right? And it turns out that if this, as you might intuitively expect, that if this sequence is stationary, this can actually is actually going to be close to what is going to be the distance on this. And actually, how we split this is by taking exponentially long chunks. So for example, for the last n/2 time steps, we choose a discretization based on this. So take it in exponentially larger intervals. So yeah, so that's the idea. We need to use the fact that there is some structure in the sequence of the side information process that ensures that these two partitions are not too different from each other. And there is a function that we are taking a mixture, that we are taking in the mixture that is close to G star. Okay.
So one quick question here.
Yeah.
Is there a formalization of this? Like this statement that if Zn is stationary, then the two partitions will not be too different?
Yeah. So basically, this is the formalization. So we say that, okay, this is kind of semi-formalization. So we say that if G has the same classification on whatever you've observed so far, the classification that these two functions are going to have on data that's coming from the same distribution is not going to be too different. So that's how we show this. We end up showing this. Yeah. Okay. So I think now I can state the main result at a high level. So there are two conditions that we need. The first is that the side information process is what I'm calling here stationary plus, which is a slightly stronger condition than stationarity, but almost the same, right? And this, you can imagine, is important because the side information previously has to give you some information about the side information that's going to come in the future. And in fact, for this one, we have a negative result that if the adversary can choose the side information completely adversarially, then there is always a strategy to break the decision maker. That there's always an adversary strategy to break the decision maker's strategy and make her achieve linear regret. Right. So this is stationarity of the side information process, and the function class G should have finite Laplacian dimension, which is basically an extension of VC dimension to more than, when you're doing more than binary classification, because we have potentially S states. And in this case, and this is of course important so that the number of atoms is not too large, because if that's true, then you can't do much, right? So then we can achieve a universal portfolio selection strategy, and it has regret that goes down sublinearly. So this strategy is universal, and the exact like asymptotics of this depend on the properties of this side information process. And so the main ideas, like we saw, was the probability induced portfolio that allowed us to convert our portfolio selection problem to a probability assignment regression problem. And then we used a data-dependent prior on the function class, refining it as time goes on. Okay, so let me just give a quick example of simulation on some real data toy examples. So if you remember the example I gave earlier of the side information class, which was using yesterday's price relative as side information and the state function as thresholds, depending on whether or not, the value of stock 1 was larger than a certain threshold. So we took like 6 years of data for Ford and Macy's. And for this case, turns out the best CRP in hindsight is buy and hold for Ford. So that achieves a growth factor of 1.11. And if you actually incorporate side information, you can do even better than that. So you can get a growth factor of 1.15. If you don't incorporate the side information, you get 0.99 or something. So yeah, so because I talked about real data, I should give a caveat, which I have not spoken about at all, which is the time complexity of this. So any mixture method, because you have to take like a sum over, if you remember, we were taking sum over exponential number of things and whatnot. So if we have that, the time complexity is gonna start becoming a big issue because doing those kinds of large operations is not feasible, especially as the number of stocks, as your state function class gets more and more complicated. So in a recent work we've been thinking about like other approaches to kind of lower the time complexity by, for example, using oracles that perform maximum likelihood estimation and seeing if we can have a low computational overhead over that. But this is definitely a very, very interesting direction. Right, so I'm just gonna revise everything we did and end the talk here. So we spoke about the universal probability approach and demonstrated how via compression, where the idea comes from, and some domains such as finance, where you can actually use it, even when you have like more modern problems, when you're incorporating side information because so much data is available and so on. And of course, like a very interesting question to me is, if you have any ideas for more application domains where such ideas can be used, I think I would love to chat about that. And we spent a lot of time talking about portfolio selection, where we saw the power of the mixture approach. But I also, like I said, a really like prohibitive thing that, for example, makes these universal portfolios type methods not that adapted in practice is the time complexity can be really, really high, so they're intractable. So I think one really, really interesting direction is whether we can have some, nice optimization-based methods that can lower the time complexity. Right, so that was my presentation. Thank you so much for listening.
Thank you very much.
I'm happy to take questions.
May I ask a question? One more.
Yes, of course.
Yeah. Now, if you were to replace the mixture by the maximum likelihood parameter, so that computationally is horrendous. But is there a significant difference in performance one way or the other? So in other words, you don't mix, but within each class or within each atom as you had, you alluded to it towards the end, you just take the maximum likelihood estimate given the data, right? And it's a messy thing because it varies with the data, of course, and you don't have a sequential way to compute things. But as a benchmark, does it give anything useful?
I haven't considered MLE, but I have seen other papers where they've actually shown that for these, entropy risk type problems, sequential probability type problems, the MLEs actually can be provably suboptimal in some cases, especially when you start considering really rich function classes.
Mhm.
So yeah, there are some results there on the suboptimality of MLA.
I see. It's also true in some cases, I think, that they don't differ by much, because you can actually bound, in some sense, the difference between log 1 by the maximum likelihood probability minus log 1 by the mixture,
Yeah.
and then mixture probability, and then that tells you they are close in some sense. But there could be applications where they disagree significantly. Yeah. But in these applications, you haven't tried it out.
No, not in this one. No.
All right. Thanks.
Any other questions? Sasha says it was a good talk.
Yeah, I thoroughly enjoyed your talk. I'm sorry I came a few minutes late. I got stuck in Washington, D.C. traffic, but I enjoyed your talk. Thank you very much.
Thank you. Thank you.
Very clear.
Thank you. Thank you. I'm glad you liked it. Yeah.
So let's thank the speaker again. And
Yep.
All right. Thank you. Thank you, everyone. Enjoy the weekend.
Yeah, you too.
You too. Thank you.
Bye.
Have you again sometime. Yep.
Yeah. All right. Bye-bye.
Bye.
Bye.